Next reaction of carbon-carbon triple bond. Next reaction of carbon-carbon triple bond is the halogenation. First reaction that we have to study, the halogenation of carbon-carbon triple bond. In case of carbon-carbon double bond, halogenation reaction of carbon-carbon triple bond. Triple bonded compound halogenation takes place in some different way than the carbon-carbon double bond. In case of carbon-carbon double bond, reaction takes place via one intermediate we call halonium ion. But here that halonium ion is a cyclic ion. Halonium ion is a cyclic ion, and that cyclic ion is not possible in case of carbon-carbon triple bond. In case of carbon-carbon triple bond, this cyclic halonium ion is not possible. That's why the process takes place via halonium ion only. Vinylic cation only. Process takes place via vinylic cation. Suppose we have taken example here. So see the example. CH-3 C triple bond CH. So we have taken here propylene. Propylene for addition, where we are adding here Br2. Okay, addition of Br. So addition of Br, where the addition of Br takes place, the polarization of Br, addition of Br2, polarization of Br takes place by when electron density gets transferred here. Polarization of this halogen takes place. So here CH3 C triple bond. Now this addition takes place according to Markovnikov's rule. What Markovnikov's rule says? It says that negative part of the reagent attaches to that carbon atom which is having less number of carbon atom. So see here CH3, this Br attachment takes place. We get positive charge here at two carbon-carbon bonds H, and Br gets attached here. So in the next step, this Br minus attacks here, and we get the dibromo propane as a product. C here Br H. Okay, so 1,2 dibromo propene as a product. 1,2 dibromo propene as a product we obtain. We have taken here propyl as a reagent, propyl as a reactor. Now propyl, when the pi electron density transferred here, the attachment of Br leaving behind vinylic cation. So there is this vinylic cation formation takes place here. This vinylic cation form where to this positive charge, this residual Br minus attacks on this positive charge, and we get 1,2 dibromo propane. But reaction doesn't stop at this stage. The another molecule of Br, another mole of Br attached here, where the process takes place in this way, where CH3 C Br, the attachment of Br here H, and now in the next step the residual Br minus which attacks on this carbocation, and we get the product. We get product here 1122 tetrabromo. Here 4 bromine atoms are there. Tetrabromo propane, saturated compound. So we obtain this product. So this is halogenation reaction. In the halogenation reaction, this is general reaction where we obtain the product. So I am writing here general reaction. So general reaction says that when we have taken this triple bonded compound, then addition of 2 moles of Br2 required for this reaction, where we get the addition of this 4-bromine across carbon-carbon triple bond. We get the 1122 dibromo tetrabromo-propane as a product. This process takes place in 2 steps. So this is step 1, first step, which is a slow step, and second step is a fast step. So these 2 steps again repeated, and we get the final product. So this is halogenation reaction. In case of alkene, halogenation reaction takes place via formation of halonium ion, where in case of alkyne, this halonium ion is not possible due to carbon-carbon triple bond, and that's why this process takes place via vinylic cation. So this is all about halogenation reaction. Now next reaction we have to study halogenation reaction. Next is the addition of haloacids. Next reaction we have to study is the addition of haloacids. See the addition of haloacids. Second reaction we have to study is the addition of haloacids. Addition of haloacids. Haloacids HX, where it is the general form, where it may be HCl, HBr, HI. This is the reagent haloacids. These haloacids reacts with carbon-carbon triple bond. Now see carbon-carbon triple bond. See the general reaction where 2 types of reactions are there. 2 types of reactions, where in first we have taken symmetrical alkene. 2 types of reactions are there. First we have taken symmetrical alkynes, and second unsymmetrical alkynes. These 2 different reactants gives the different products. Symmetrical alkynes. In case of symmetrical alkynes, we obtain only one product, and in case of unsymmetrical alkynes, we obtain 2 products. One product is a major and another product minor. In smaller quantities, in minor quantities, we obtain another product. So unsymmetrical alkene, 2 types, symmetrical alkenes and unsymmetrical alkenes. So let's see first symmetrical alkynes. Symmetrical alkynes react here. See symmetrical, we have taken example here, symmetrical alkynes. See CH3. These are symmetrical alkynes. When react with, suppose HBr, reacts with HBr. Okay, so react with HBr. So due to symmetrical alkene, hydrogen may attach here or to another. It remains same. In next another mole, CH3 H, here H, and here 2 moles of Br obtained. Okay, 2 moles of Br added here, 2 moles of hydrogen added here. So this is general reaction of symmetrical alkenes, where we obtain single product. We obtain single product. When we obtain single product here, so that we have taken 2 butane as a reactant, and hydrogen bromide addition takes place here. Here we obtain 2 bromo butane as a product, and here 2 dibromo butane as a product. 2 dibromo butane as a product. So this is symmetrical alkyne. When symmetrical alkyne is there, we obtain only one product. See the mechanism of this reaction. Where we use symmetrical alkyne, where we are using symmetrical alkyne. In this case, symmetrical alkyne. See, first step is the formation of vinylic cation. Carbon-carbon triple bond is a source of electron. where it attacks on the partial positively charged hydrogen. So it attacks here and a residual Br minus generation is there. So CH3, this is first step and it is a slow step where vinylic cation formation takes place. So here vinylic cation formation, C double bond C, here cation formation takes place, and here attachment of hydrogen, CH3, and in the next step the residual Br minus attacks here and we get the product. So CH3 C and here Br double bond H CH3, we get the product, and in the similar way another mole of HBr gets added and we get the product 2,2-dibromobutane. We get the product 2,2-dibromobutane, where the attachment of this Br minus or attack of this Br minus is the second step and which is a fast step. Okay, so this is the mechanism of addition of haloacids with symmetrical alkenes. Okay, symmetrical alkynes. Here symmetrical alkynes we have taken in the first step. The pi electron density shifted to accept this H plus. When this H plus gets accepted by the one of the carbon, another carbon leaves with the positive charge. We call it vinylic cation. Vinylic cation. So this process is also takes place via vinylic cation formation. So vinylic cation formation takes place, and there is a attack of attack of this nucleophile of this carbocation, and we obtain the product where in the similar way it reacts with the another mole of HBr to obtain the final product. So this is in case of symmetrical alkyne. Okay, if instead of that if we take unsymmetrical alkyne, then what is actual procedure? Here we obtain two products, one is major, one is minor. How this happens? Let's see in the mechanism. Unsymmetrical alkyne. See the addition of HBr to unsymmetrical alkyne. See here, I have taken another unsymmetrical alkyne. See, addition of halacid to unsymmetrical alkynes. Unsymmetrical alkyne, I have taken an example here, CH3 C triple bond CH. This is unsymmetrical alkyne. Okay, this is unsymmetrical alkyne, where unsymmetrical alkyne addition of HBr is there. We obtain two products. Which two products are obtained? Let's see the mechanism for this one. See, this is the reactant alkyne. When reactant alkyne reacts with HBr, one of the bond shifted here, so that production of Br minus. When one bond shifted here, this double bond is attached to two carbons. This carbon and this second carbon also. This double bond bond attaches to two carbons. Now this hydrogen, when the electron density shifted to accept proton, the hydrogen gets attached to one of the carbon. Out of these two carbon, one carbon attached to this hydrogen. So one carbon attached to hydrogen, but bond leaves from two carbon. So another carbon leaves with a positive charge, deficiency. So see here, CH3 C. Now this carbon leaves with a deficiency, but when the hydrogen attaches to this carbon, this another carbon leaves with deficiency. So see here, two possibilities are there. See the first possibility, when CH3 C double bond C H, and this hydrogen if attached here, then positive charge shifted here, positive charge here, hydrogen attached here. Another possibility where CH3 C double bond C H H, sorry, instead of this hydrogen attached here and positive charge goes on this carbon. What goes on this carbon? Let's see the stability of this one. Stability of these two carbocation. The carbocation formed here, this vinylic cation. So, which is more stable? We know that positively charged atom is stabilized by electron donating group. Okay, electron donating group. So here plus I effect group is there, but here only hydrogen is there to stabilize this positive charge. But here carbon CH3 group is there, which is having plus I effect. So due to plus I effect of this carbocation is more stabilized. So more stabilized carbocation, in the next step, the attack of the nucleophile. Nucleophile attacks here, and we get the product, that is CH3 C Br double bond C H H, and here again another mole react to form CH3 C Br double bond, sorry, single bond CH3. So in this way we obtain this product as a major product. Major product because of stability of this carbocation, vinylic cation. Stability of this vinylic cation, we obtain the major product. This one is a major product. In case of this C, in the second step, this nucleophile attacks here, and we get the product CH3 C H double bond C. Here is Br and attached hydrogen. In the second step, second HBr, mole of HBr react with this, so we obtain CH3 CH double bond, sorry, single bond CH3C so we obtain this one as a major product. This one as a major product. In this case, we obtain major product. Sorry, this one is a minor product because here we are attached to less stable vinylic cation. Here more stable vinylic cation, we get this product. Sometimes question they may ask, when unsymmetrical alkene, when unsymmetrical alkyne react with haloacids, it gives two products, one major product and minor product. Explain with suitable example. So you have to take an example, any example, not only this. You can take another unsymmetrical alkyne which react with this to obtain two products. So in general reaction we can write, when this alkyne reacts with this propyne react with HBr to obtain CH3C Br CH3. So here 2,2-dibromopropane as a major product. So this is major product here, and plus we obtain another in smaller quantity. The product is a CH3 CH2 CH3, I'm writing here above, plus we obtain CH3 CH2, this product CH Br. So 1,1-dibromo